Okay, we're doing friction again. Oh, that sucks. Actually, not that bad. It's really, really not. I'm going to leave a couple of our definitions up here. These we don't need, because this was just part of solving the problem. Whoops, that was a text box. I meant to use this selection thingy. They should not look so similar. I don't like that. We don't need the diagram, because we're working on a different problem. I'm going to leave this, and I'm going to leave all these definitions here. I don't know what the hell that is, but it keeps popping up, so... unknown process that I should probably care about, but I don't care. So, what do we have here? Okay, so what we're going to do here is, we're going to say that there's this box, right? Let's make a sixth floor, and we've got this box, right? And we're going to say that this box has a mass of 10 kilograms, right? 10 kilogram box. And we're going to say that it starts out moving, say, this direction at a speed of 8 meters per second. Now notice it's not accelerating, so in fact it's actually going to be slowing down because of friction, right? Just like if you start out moving at some speed, or if you start out, well, not you, but if you roll a bowling ball at some speed because of friction, or not a bowling ball, if you slide some block at some speed because of friction, eventually it's going to slow down. Or either eventually it's actually going to come to a stop. It's going to constantly be slowing down. So let's say that it starts off at that speed, and then that it travels. Let's make this. How do we make this right here? 45 meters. I think this might actually be what the example problem was. Hold on. Okay. So it's traveling 45 meters. So maybe what they'll ask you for, they could ask you for the coefficient of friction, or they could ask you for the mass and give you coefficient of friction. Okay, they give you the mass. Maybe what they'll ask you for is, maybe they'll say, okay, what is mu? What is our coefficient of friction? So in this case, that's what we're going to solve for. And keep in mind that maybe they gave us mu, and they want us to solve for the mass. It's the same process. What you want to do is you just want to solve in a different way. You still plug in all the same numbers, except you're just solving for a different variable now. So I'm just going to say that right off the bat. So how can you start this out? Well, first let's kind of think about it. In the case of a system where energy is being lost because of friction, it's losing energy because of friction. We have the mechanical energy minus whatever work friction is doing. So minus the energy that's being transferred out of the system because of friction. It actually turns into like heat. But when you take the initial energy minus the amount of energy lost because of friction, then you get the final energy. So that's a more full version of the equation. Hold on. That's a more full version of the equation, I guess. That's, again, relatively simple. It's kind of common sense. But there you go. So what is our, what's our mechanical, our initial mechanical energy? Our initial mechanical, oops, that shouldn't be a capital I. Our initial mechanical energy equals the, it's the kinetic energy plus the initial gravitational potential energy plus the elastic potential energy. So, it's at zero height, right? It's not floating up in the air somewhere. The gravitational potential energy is zero. There's no springs or rubber involved, so the elastic potential energy is zero. So it's just equal to the kinetic energy, right? Hopefully that didn't confuse anyone. Just these two values are zero, so these can get scribbled out, and we just have the mechanical, the initial mechanical energy is equal to the initial kinetic energy. So that's equal to the initial kinetic energy right there. And what's the final mechanical energy? Well, You can think about this in two ways. One, you could go and say, okay, elastic potential energy, obviously 0. Gravitational potential energy is at 0 height, so that's 0. Kinetic energy, it's not moving, so it's 0. Or you could just say, okay, it's just sitting there. It's not doing any work. It can't do anything. 0 energy final. That's the 0 mechanical energy. The 0 is a total. So what do we do next? We pause the video and then I continue in a sec so I can answer a text. Okay, back to what I was doing. I love that pause feature. I never noticed that was there, that stupid little button. But, okay. So we figured out that the final energy is just whatever the energy started with minus whatever work friction is doing. Basically, if you take however much energy the system started with, subtract how much energy friction is taken away, you get what energy you end up with. So the initial mechanical energy we said was equal to the kinetic energy, the initial kinetic energy. So then that minus the work of friction equals, well, the final mechanical energy. That final mechanical energy we said was 0. Let's expand this text box. So now, what we need to do, we need to start plugging crap in for this. Except what we can actually do is we can say, let's subtract the work of friction from both sides, and then we get that the initial kinetic energy is equal to the work that friction does, or the frictional energy, so to speak, the energy lost because of friction. So how do we go about doing this? Well, kinetic energy we know is, let me write this in. It's the mass, kinetic energy. Oh, yeah, I'm not going to do that. So we have the mass times the velocity squared over 2. And we have that being equal to, well, what is the work? Work is the force times the distance, right? So, force times the distance, or distance times the force. So distance times the force of friction, right? It's acting over 45 meters. Distance, or force times distance, and that's equal to 45 is the distance, right? That's how far it's acting for. Times what's the force of friction? What? How do we come up with the force of friction? That we learned in our last chapter. That was our normal force times the coefficient of friction, right? That's our normal force times the coefficient, which is our mu. And now it looks like we're getting close because we finally have that mystery variable that we're looking for. So one more thing that we kind of want to look at. What is the normal force? Well, in this case, actually, since it's just a flat surface right here, you might get an angled surface, but hopefully by now you know how to how to find the normal force on an inclined plane. But in this case, it's just a flat surface because I want to make the example easy enough. So the normal force is just going to equal to the weight, right? Because if it's being pulled down with some amount of force because of gravity, the surface has to be pushing back up with the same amount. And if we take 9.81 times 10, we get 98.1, right? Well, I didn't write that. I didn't write that correctly, but we get 98.1 as the weight, or the normal force. So we get 45 times 98.1, and that's that mu there, that mu that we got there. Hopefully I'm not like drastically screwing this shit up, because if I am, I'll be kind of sad. But we'll see. I kind of have a reputation for that though, so don't count on it. Okay, so let's plug in our values for M, V, and M and V. Our mass is 10. We have 10 times, our velocity is 8. So we have 8 squared. And that's over 2. So this, you can see this you cancel that and you get 5, right? Because 10 divided by 2 is 5. So 5 times 8 squared. 8 squared is 64. And then 64 times 5, you get 320. 320. So 320, that's the kinetic energy, right? We figured that with the kinetic energy equation. But we also figured out that the kinetic energy has to be the same as the work that force is doing, right? Because force is bringing it to a complete rest. Force is getting rid of all this energy that it started with, this friction. That's also equal to the work of friction. Cool stuff. Okay, so it's also the work that friction is doing, right? 320, and it's joules. It's the same unit. So the work that friction is doing. We said the work that friction is doing. It's kind of ugly right here, but it was this, and then we plugged a couple numbers in. We plugged in the equation for the frictional force. It was this, and then we ended up getting this. So we get 45 times 98.1. Let's just calculate that. 45 times 98.1. We get 44145. Okay. 4414.5. Right? Was that right? Oh, I don't know. I accidentally closed out of it. Oh well. I think that was what the number said. And I probably shouldn't have that many decimals, but honestly, I don't care. I'll round at the end. So it's that times mu, and this, if you can't solve the equation 4,414.5 times mu is equal to 320, if you can't solve that, go back to like pre-algebra, because that's really simple, right? So, whoops, wrong window, handy dandy calculator. So we'll just divide both sides by this thing, right? 4 da 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 da. You divide this by the 4 da 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 da. You divide it by all that crap. So when you divide this one, this cancels out, right? Because those are the same numbers. You just get mu. You get mu is equal to 320 divided by 4,414.5. 0.5 probably didn't make a difference. We get 0.0045. Mu is equal to 0.0045. And let me see something. Let's see. What's 350 divided by? Sorry, I'm just making sure that my work is correct, because I constantly worry that I give you guys the wrong answer, or rather, the wrong method of doing something, because then I feel bad. What did I do wrong? Yeah, did I do anything wrong? I can't tell. This is moderately strange. I think I multiplied this wrong. I think I got a really wrong number when I multiplied that. That was not 15, was it? That was 45. Let's do this again. Angela is laughing at me right now. So 45 times 98.1 equals... Nope, that's the 4414. So 4414 times u equals 320. Am I screwing something up? I hope not. So, inverse of that times 320 equals... Okay, I guess I just did that division wrong. 320 divided by that 4415, or I'm sorry, divided by that 4414.5 equals, not this, it's 0.072. 0.072, that looks right. I don't know what I typed in the calculator. Maybe you can go back and look at the video and see what I messed up typing in the calculator, but I'm probably over time by now, which I really hope I'm not, but I'm going to be making another video pretty much right now, and it's going to be on, what am I doing in the next video? Let me look. I think I have no idea what I'm doing in the next video. I know what it is, but I don't. So, I'll see you then.